Okay, peeps, last re-recording. This is where we left off. This was the last lesson before we went on our winter break, and it was 6.5, which was using our knowledge of transformations and transformation notation and the mapping rule to sketch transformed sinusoidal functions. And so, just as a quick little reminder, again, to drill it into your brain, since you're going to need this on the test, we use transformation notation or the letters A, K, D, and C. You've been using them throughout the whole course, and you've known what A, K, D, and C are responsible for in terms of the other parent functions. But when it came down specifically to sinusoidal functions, they had their own key characteristics they were associated with. So as just like a quick little run through, we said that A, which is usually in charge of like vertical stretches and compressions, this was now our amplitude, which we could calculate as max minus min divided by 2. And like I said, I'll make the little note here that this was for vertical stretches and compressions and reflections in in the x-axis. K is the period of the sinusoidal function, and we said that you can use this basically in two different ways. So for example, if you need to determine the K value for an equation, if you're given a graph, you can say that K is equal to 360 divided by whatever the period is, which if you're given the graph, you can kind of visually determine it yourself. Or if you have the K value, but you need to graph the period of the sinusoidal function, you can determine that the period is going to be 360 divided by whatever your K value is. And we said that this value on other parent functions represented horizontal, I don't know if I'm going to have room for this, horizontal stretches and compressions, as well as reflections in the y-axis. Moving on through, D was same old. It was now called a phase shift, but it's always been in charge of shifting, specifically left and right. And we said that if it was X plus D, then we would be moving left, and D is actually in the negatives. And then X minus D would mean that you're moving right, and that D would actually be in the positives. That has always stayed the same. So your horizontal shift has always been associated with D. And then last but not least, you've got C, which in sinusoidal terms, this is always referred to our equation of axis or midline, whatever you want to call it. And we can calculate it using max plus min divided by 2. And this was usually associated with our vertical shift up and down for the other parent functions. So we have practiced not only describing sinusoidal functions in terms of like the regular parent function transformations, in terms of stretches, compressions, shift left and right and up and down, but we've also now associated those same letters and parameters with now the sinusoidal characteristics like amplitude and the period and the phase shift and so on. So we're going to get into actually practicing graphing these transformed functions from their parent function and using the mapping rule. So for example, we've got here, we need to sketch the graph of f at x, which can be modeled by or represented by 3 sine 2 bracket x minus 60 degrees bracket plus 4. We also need to graph the parent function on the same axis. So okay, we need to first think about what are my 4 special letters. What is A, what's K, what's D, and what's C? Because those are the things that we're going to need for the mapping rule. So okay, step 1, we need those parameters. Luckily, I don't have to do any extra factoring for this equation. K is already on its own, so I don't have to do anything there. So I'm just going to be moving left to right. So I can see that my A value is going to be 3. My K value is 2. my D value, since it is minus 60, that means I'm moving right towards the positives. So this is going to be a shift positive 60 degrees, right? And then lastly, my C value at the end is positive 4. So, okay, I've got a value for everything. So when it comes to my mapping rule, right, which I will remind you, mapping rule, the general formula we said is x over k plus d, ay plus c. So if I just now customize this to these parameters, my new rule is going to be x over 2 plus 60, and then 3y plus 4. That is now my new mapping rule specific to this graph, right? And when it comes to your anchor points, right? Or if you remember from way back when in Unit 1 and also in Unit 4, when you had to graph like the square root function, the absolute value function, the exponential function, we had anchor points, or just 3 points from the original graph that we could send through the mapping rule in order to give us a somewhat accurate idea of like what this curve is going to look like now that it's been transformed or has undergone these specific transformations. For your sinusoidal functions, you are going to have more than 3 anchor points. Ideally, you would like to get in one full cycle, and you want to see how that changes. So if I can remind you, or you can remember that you're going to do the 90-degree increments from 0 to 360, and you can just plug those into your calculator. So for example, for the anchor points for f of x equals sine of x, right, the original function, if you plug in 0, you will get 0 back. If you plug in 90, you will get 1. If you plug in 180, you will go back to 0. 270, you will go back to -1. And then 360, you will return to 0. So you're going to be oscillating only between 1 and -1 for your parent function. And again, this did not require me to memorize these points. I feel like you will eventually just have them memorized from doing it so often and kind of remembering the shape. But when in doubt, use your calculator to determine these points, right? Just do 90-degree increments from 0 to 360. That is more than enough. I'm going to go ahead and graph those anchor points in pink on this graph, since we have to do it as well. Because this looks like we're shifting upwards, not only 4, but we're also having to be stretched or have an amplitude of 3. I'm going to do each cube representing 2 units. So this will be 2, 4, 6, 8, and I'm hoping that that's enough room. Same thing here, -2, -4, -6, and -8. So that should be enough. So, okay, you're going to see that this is going to be like a very wide parent function just because of the scale. So again, 0, 0. At 90 degrees, I'm at 1, so I'll be halfway here. 180, I'm back to 0. 270, I'm at -1. So again, I'm at that halfway mark on the square. And 360, I'm back at 0. So you can see this is a very stretched out version of sine of x. Right, so that's your parent. So when it comes to now the transformed graph, right, the one that we're given in our original equation, we're going to use the mapping rule. And you're going to see that this process just becomes very redundant because you're doing the same thing over and over again. However, you let the calculator do the heavy lifting for you, right? So there's nothing that you have to memorize or any special rules on your end. It's literally just plug and play. That's basically it. So, okay, referring to the mapping rule up above, I'm going to plug in 0, 0. So my x is 0 and my y is 0. Those are the only things changing within the mapping rule. So this is going to be 0 over 2 plus 60, and then 3 times 0 plus 4. And when you calculate that, 0 divided by 2 is just going to be 0 plus 60. That is going to give me 60 degrees as my starting point. And then 3 times 0 is 0. So just plus 4. That will be my new 0 point, 64. And I'm going to just keep repeating this. And I'm even going to space out. Give yourself some room to do all these points. Right? Might as well. Oh my God, I can't get the corner. There we go. Okay, now that I'm like a little spaced out, I'm going to just keep repeating. So, okay, I'm going to do 90 all over 2 plus 60. And then 3 times 1 plus 4. Again, letting my calculator do the heavy lifting for me. 90 divided by 2, that's 45. 45 plus 60 is going to give me 105. And then 3 times 1 is 3, plus 4 gives me 7. Right. If I keep running through these points, I'm going to give myself as much space as possible just to avoid super crowded work. Again, I'm going to keep repeating. 180 over 2 plus 60, 3 times 0 plus 4. You'll notice, okay, 180 divided by 2 is 90. 90 plus 60 is 150. And then 3 times 0 again is 0 plus 4. We return back to 4. So I can see that 7 is going to be my peak. It's going to be my maximum value because I've now come back down to where I started. And you'll notice that my X values, right, or my inputs essentially, are going up by 45, 60 to 105, 105 to 150. So each of these is going to go by 45 degrees, right? And you're just going to keep repeating your pattern. 3 times -1 plus 4. We will get that this point now is going to become 195, 1. And then my last point, 360, 0. Again, I'm repeating the same thing. The only thing that's changing in the mapping rule is X and Y. And when I do that, I get that my last point will be at 240 degrees, and then I'm back at 4. So my minimum point is going to be +1. So I'm completely above the x-axis here. So okay, I've got all these points. Now I just have to plot them, which I will do in this dark blue. And again, be as accurate as you can. According to the scale for the x-axis, every 3 is 90 degrees. So that means this is 30, this is 60, this will be 120, 150, and so on and so forth. 180, 210, 250. And then 270, our last point's 240, so we don't have to keep going. But you could if you would like to extend. So, okay, my first point is at 64, so I can go all the way and plot this first point. Then I'm at 105.7, so I'm going to just get in between here. 105 will be slightly after 90, but not quite in the middle. So 105, and I'm going to go all the way up to 7, which will be in between 8 and 6. Then if I go to 150, I'm back at 4. 150 is a clear point, so I'll be back at 4. Then we're going to go to 195, again, slightly after 180. So 195, and then we are at 1. And then we are going to 240, which is right before 250, and we're at 4. So right before 250, and we are back at 4. Ooh, why did I say 250? I just realized this is why we don't do 3 video recordings at once. 30 degrees would make this 240. Duh, 240. There we go. Even better. Perfect. So that is more than enough for me to trace. I can see that it does in fact make one full cycle. So, okay, I'm going to trace that. Right, and the best thing about this is that if you wanted to extend this, for example, to touch the y-axis to see like where's your y-intercept and all of that, the pattern's just going to be the same. You're always going to be oscillating between 4, 7, 4, 1, 4. Repeat 7, 4, 1, 4. Repeat 7, 4, 1, 4, and onwards. So you can extend it forwards, you can extend it backwards. You don't really have to keep doing the algebraic work or the mapping rule over and over again, because you know that this is a repeating pattern, right? It's periodic. So it's only going to oscillate between 1 and 7 every 45 degrees. So for example, if I wanted to go backwards, I know, okay, I need to go backwards 45 degrees. So 60 minus 45 is going to bring me to 15 degrees. And then according to this pattern, from 4, I should be going down into my trough, or to 1. So I know that at 15 degrees, I'm going to be at 1. So that will be my extension. And then obviously, because we don't have a negative axis here, I would be over in the negatives for my next point. So you can just try and like connect this as best you would. And that's more than fine. Same thing if I wanted to like extend it this way, for example. I know that in 45 degrees, I would have to do 240 plus 45. So that would bring me to like 285. And I know that I'm on the upwards. I should be heading next to my maximum point. So at 285, I would be at my maximum point of 7. And then in another 45 degrees, I would be heading back down to 4, right? So you would know the pattern just continues on and on the same. You wouldn't have to do any extra algebraic work. So that is our sketched graph. If I want to know, for example, the same characteristics, amplitude, period, phase shift, EOA, in this case, I can see all of those things based on my A, K, D, and C. So I'll write them down here. So our amplitude, we said, was our A value, which in this case is 3. We know that our period, in this case, we can either visually see it or you can use your K value. So in this case, if I did 360 divided by our K value of 2, that is going to give me 180 degrees. We have phase shift. In this case, we have 60 degrees to the right originally. So it's like our starting point before was at 0. Then we started our new graph at 60. So this is 60 degrees. And then lastly, our EOA, or equation of axis, is going to be at 4. Which, if you wanted to now sketch it onto this graph, you could see, yeah, 4 is where I am completely in the middle. It's cutting this graph perfectly in half. And voila. That is all. Okay, moving on to the second and final page, which is where I started to get you guys to start practicing if you could do these types of graphs. Even for example 2, we're looking at a cos function now, but it is the same exact steps of start with your parameters, A, K, D, C, define them. Step 2, use them to make your mapping rule. Step 3, anchor points. And then step 4, graph and state characteristics. So, okay, with this one, first things first, my parameters, A, K, D, and C. So just by looking at this equation, I can see, okay, my A value is my first number, which is going to be -2. My K value is on the inside, which is attached to X, so that's going to be 3. I do not, however, have a plus or minus anything in the brackets, right? So K is just kind of the only thing that's in there. So therefore, we know that D is going to be 0. I am not shifting left or right. And then the last thing that I have is a -1 at the end. That is going to be my C value. So C is -1. Now, if I'm trying to build this mapping rule, again, general form, I always like to start with just to have like as like my model, X over K plus D, and then AY plus C. Using these letters that I have determined from just looking at the equation, I can see that my mapping rule is going to be X over 3. And then you don't have to say plus 0. You can if you'd like to, but it's just saying like you're adding nothing. So just x over 3. And then a, y, so negative 2, y minus 1. And that is going to be my new mapping rule. And same thing like we did for the last one. For the anchor points for cos, for f of x equals cos x, you can use your calculator to determine these, right? So again, you're always starting at 0, you're going to 360, you're doing these 90-degree increments, and your calculator will tell you what each of those points are. So for example, if you plug in 0, you will notice, I got ahead of myself there. If you plug in 0 and you do cos of 0, you will get 1. So different starting point than sine of x, right? Same thing. I'm going to just keep going, and I'm going to do cos of 90. You will notice that that gives you 0. Same thing, 180. That will give you negative 1. 270 will give you 0. And 360 will bring you back to your initial starting point of 1. So, okay, and I'm going to give these a little shift up since I don't have as much room as I thought I would. And you're going to do the same thing that we did with sine, which is send these points through the mapping rule. The only thing that's changing is your x and your y in the mapping rule. So for this first point of 0, 1, this is going to now be 0 over 3, comma, negative 2 times 1 minus 1. That is going to give you 0 divided by 3 is just 0. And negative 2 times 1 minus 1 is going to give you negative 3. Done. Point determined. And you're repeating. So again, 90 is going to be our x, 0 is going to be our y. I'm going to replace those in the mapping rule. So this is going to really be 90 over 3. And then negative 2 times 0 minus 1. And that gives us 30 degrees and negative 1 as our y. And I'm just going to keep repeating. Now 180 over 3. Negative 2 times negative 1 minus 1. You'll see this gives us 60 degrees. And then our y value is going to be positive 1, which is the highest value we've had so far. And I can see already that each of my points, rather than going up in 90-degree increments like we started with on the parent function, I'm going up by 30-degree increments. So my points are kind of closer together. And we repeat, and this is the most tedious bit of the unit because it is just repetitive over and over again. You're doing the same thing. This is now going to be 90 degrees, negative 1. And last but not least, if we send in 360 into the mapping rule, we are going to get 120 degrees, and this will leave us with negative 3. So negative 3 is our minimum value, and positive 1 is our maximum value. Again, I'm going to do the same thing like last time. I'm going to graph the parent function since we have to... this one actually doesn't say to graph the parent function, but we did in class, so I'm going to stick to what we did in class. I'm going to use a different scale because I see that we're not really shifting up or down that much, and our amplitude is not super high. So I can actually make this scale 1, 2, 3, 4, and negative 1, negative 2, negative 3, negative 4. And I will do the parent function in pink, so the regular cosine function. So for the original anchor points that we see here, I'm just going to plot those. So we said 0, 1, 90, 0, 180, negative 1, 270, 0, and 360, 1. So this is our original parent function. And I will write that f of x equals cos x. And then when it comes to our transformed function, I'm going to do that in the dark blue. So I'm just going to use these for reference. So, okay, at 0, I'm now actually starting at negative 3. At 30 degrees, which will be my first box, I'm at negative 1. Then at 60, I reach a maximum of 1. At 90, I go back to negative 1. At 120, I'm back at -3. And that already is going to be one full revolution. So I was able to do like one full revolution in a third of the time compared to cos of x, right? And again, like I said for the other one, if you wanted to extend this graph, phew, bless me. If you wanted to extend this graph a couple other cycles, you don't have to do the parent function, You don't have to do the mapping rule over and over and over again with new points. Now you know that this is still going to just oscillate between -3 to -1, 1, -1, -3, repeat. And you're going to keep repeating that cycle. And you know that this is going to be in 30-degree increments. So hypothetically, if I wanted to extend this, 30 degrees after 120 is going to be 150, and I know I should be going back up to -1. In another 30 degrees, I should be hitting my max. So at 180, I'm going to hit 1. And in another 30 degrees, I'm going to be heading back to -1. And therefore, in another 30 degrees, doing another 120-degree rotation or period, I'll end up back at my minimum value of -3. And look at that. There is another full cycle, right? You can continue doing this. I didn't have to do any math there. That was just me counting the pattern, essentially. And that's it. And then last but not least, we have to do the characteristics right before I'm running out of room. So the amplitude in this case is our A value, which is 2. We don't have to say -2. The negative is just implying that there is a reflection in this case in the x-axis. So that's all it means. It means like the reflection. We don't have to say the amplitude is -2. When it comes to the period of this function, again, we calculated it. We know it's 120 degrees. So you can write that, or if you wanted to visually determine or algebraically calculate it, you could say that it's going to be, oh my, 360 all over 3, which is our k value, which does give us also 120 degrees. So visually from the graph, you can determine it. Algebraically, you can determine it with the 360 over k equation. Our EOA in this case is our C value, which is y equals -1. And if you wanted to sketch it again on this graph to like see that the amplitude works out, you can. There is no phase shift in this case because we are starting at the minimum, right? We don't have to shift over any sort of left or right in any direction in order to start at the minimum. We're already at the minimum for negative cos. So therefore, there's no phase shift. And then last but not least, this question asked for the range of the sinusoidal function, which, throwback to Unit 1, range is just saying like what y values is it allowed to take on, or what y values does it exist between. In this case, it is between 1 and -3. So we're going to say YER such that it is basically sandwiched between -3 and 1. That's your range. It's oscillating between those. Okay, finally, we reached the end. This was the one that I sent you all to do on your own to see that if you could figure it out. This one's got a little bit of a wacky scale. So before you even try to maybe like pause the video and attempt it on your own, I would just extend a little bit on both sides. So we would need at least 1, 2, 3 to go to -90, and then I believe 3 more on this side. Ooh, to go to 450. So 1, 2, there we go, 450. So I would recommend pause this video, try it on your own, see if you can get the same shape. For those of you who want to follow along with me, we're going to follow the same step as above. However, you might notice those brackets look a little interesting. They look a little sussy. We need to put K by itself. K needs to be by itself. We need to have a double set of brackets before we can say what A, K, D, and C are. So step 1 is actually, we need to factor that to find K. So this is really going to be f of x is equal to negative sine, and I'm going to factor out 0.5. And when we do that, we're going to get x plus 90 degrees, right? So it's always important to double and triple check to make sure that you are factored in the inside and you've got that double brackets if necessary, right? K should always be by itself, because if we do not factor, that is going to change what we are shifting left or right by, and sometimes even the direction, right? So, okay, in this case, it's factored, it's done. I can now clearly see that my A value is -1. My K value is 0.5. My D value is now negative 90, since it's plus 90, so it's not going to be 45. And then you'll notice that we do not have a C value in this case. There's no plus or minus anything at the end of this equation, so that just means we have not shifted up or down. Our midline is going to be going through 0. That's all. Once we've got that, we now need to do our mapping rule. Which again, if I'm doing the general form of x over k plus d ay plus c, using these specific parameters, I know that this is really going to be x over 0.5 minus 90, and then I'm going to have negative y. I don't have to say plus 0, so that's it. That is the end. All of our y values are essentially flipping and becoming negative. And then comes to using the anchor points. And we are doing this for sine. F of x equals sine of x. Again, you might have them memorized by this point, or you may just have to use the calculator, either or. I'm going to give these a little scooch up just to give myself some room, and maybe even make them a slightly smaller. There we go. Right? But if you just need them quickly, they are 0, 0, 91, 180, 0, 270, -1, and 360, 0. Those are our points for sine. And those are the ones that you are going to send through the mapping rule. So even if you want to now pause here, if you're comfortable enough with how far we've gotten, try finishing the mapping rule by yourself. See if we get the same thing. Otherwise, you can keep following along with me. This is kind of a short mapping rule. You'll notice that nothing much is really happening to our y coordinates. Everything's happening to our x. So for example, the first one, 0 over 0.5 minus 90, and then -1 times 0, you'll be left with negative 90 degrees at 0. I'm going to keep repeating. So 90 divided by 0.5, which is also like saying like 90 times 2. And then minus 90. -1 times 1. That is going to give us positive 90. And then -1. If I go into 180, again, 180 divided by 0.5 is like saying 180 times 2, and then minus 90. And then again, -1 times 0. You'll see we're all the way at 270 now. And then back at 0. So, okay, our increments are going up by 180 rather than 90. So it's like we're doubling the size. And if I keep going, you'll notice the same pattern continues. And in this case, if we are doing 450, -1 times -1 is going to give us +1. So that's going to be our maximum point. And 360, I don't even think we have room for on our scale, but we'll just do it for the sake of finishing the mapping rule. Yeah, see, we'll be all the way over at 630 degrees, 0. So that is gigantic. And if I go to plot the original, which I will do ones by my scale, so -1 and -2. Again, doing the parent in pink. This is my parent function, 0, 1, 0, -1, 0. So that is my original sin x function. And now if I do in blue, my new transform function, you're going to see that this is super wide and barely covers one full rotation or one full revolution. So at -90, I'm at 0. All the way to +90, I'm at -1. All the way to 270, I'm back at 0. And then at 450, I'm at 1, which is like approximately there. So I didn't even get to do my last point to make it a full cycle. But you'll see that this is so wide, right? So that's my new transformed function. And in this case, it did not ask us to state any sort of special characteristics, but I always like to get in the habit of doing it just to state it, just to be sure. So you can take the time to do that, but you'll see that transformations of sinusoidal functions, there's no need to be overwhelmed or scared because it is just the same concept that you've been doing the entire semester all year long so far. Nothing has changed. It's just the fact that now we're using degrees instead of a regular number. So that is it. That's where we left off. We're officially caught up. I'm never going to leave my microphone off ever again because this was very painful recording 3 videos back to back. This will be up and posted and ready to go. And you only have 2 lessons left of this unit that we're going to finish by the end of this week. And then you are done grade 11 math. So pat yourself on the back and crack out those old Unit 1 notes because we're going to get to studying and prepping for the exam next week after your test for this. So good luck. I'll see you tomorrow, and I hope you had a restful winter break.